Something simple like you did for 410. You're not doing that this semester.
I'm doing that.
Oh, you are?
It does it automatically on Canvas.
Okay, because I was looking at the syllabus and I think I might have missed it or something. But
Oh yeah. It might not be in the syllabus, but it's in the first presentation. But yeah, I do that every semester.
Oh, yeah. Awesome.
Mhm. Yep.
So I have one question regarding the activity vibration. So first is, the in 3, 3, 4, 5. So do we have to perform both the stress-free and free stress or just one condition?
Just one.
Just one thing.
Yeah.
And second thing regarding the material force, I'm going for the stress-free.
Yeah.
And for the stiffening material, I choose the tungsten.
Okay.
As it has, I guess, 4 energy general models. And for the second material, like for the stress, should I select any plastic material or actually metal?
Yeah, it could be plastic. That's fine. Yeah. So you can use polyethylene. I think that's both in it. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? Hanging in there? It's almost finals week, I know. But today is our last ANSYS activity, and so maybe that's a good news, maybe that's bad news. I'm not sure, but it's news, I guess, nonetheless. Right? For me, it means that I don't have to prepare any of these anymore, and that's a good thing. So these actually take me quite a bit of time to actually prepare. So it's this is more ANSYS activities than I've ever done in a class before. So this one and the last one are actually brand new ones. So I'm kind of, it's bittersweet that we're at the end, because I enjoy doing these, but they're also kind of a lot of work too. All right, and so today we're doing basically a continuation of what we covered on Monday, which was buckling analysis. Okay, and so I've found this this truss geometry for you. Okay, and so it's basically a truss assembly. Okay, and we're going to see how the buckling analysis works in ANSYS. Okay. And we're also going to observe the stress stiffening effect. Okay, so we'll actually see it being applied in practice, and you'll see how the stress stiffening effect affects the deformation in a structure like this. Okay. Okay, and so if you haven't already, then I would go to the Canvas site, and then if you go to the assignment page, you can download the instructions for the activity today, as well as the CAD model. Okay, so the CAD model should be 3dtruss.agdb, which is a design modeler file. Okay. All right, and so before we get started, are there any questions I can answer? Okay. All right. Oh, and the due date for this will be next Friday. Okay, so it'll be next Friday at 11:59. Okay? But I'm hoping that this activity doesn't take too long. There's everything is just kind of like let's try things out. And so there's not a lot of having you guys do a lot of work on your own, and the amount of time it takes for these simulations is very small too. So I think hopefully it shouldn't be that big an issue. Okay? All right, and so we're going to be doing a buckling type analysis. Okay, and so if you go ahead and open up Workbench, okay, right, and you download the file, and our starting point for the analysis today is going to be static structural. So let's go ahead and drag static structural and drag it into the workspace here. Okay, and then let's go ahead and import the geometry. Okay, so let's go ahead and import. I think it went straight to my downloads folder. Yep, 3D truss. Okay. And then we don't need to do any modifications on this because the geometry has already been converted to beams. Okay, and so the only thing we have to do is just open up mechanical. So let's go ahead and double click on model, and we'll open up mechanical first. All right. And so our first step is going to be static structural, and we'll actually be here for quite a bit of time, before we actually get to the eigenvalue buckling. Okay. Because first of all, we have to set up the mesh and the boundary conditions just like we normally do. And we're going to use static structural to actually observe what the stress stiffening effect looks like. Okay. All right, so I'll give it a minute or two just for workbench or mechanical to start up. Mine's being a little bit slow. Okay. Okay. All right, and so here is our geometry, and so you can see it's it's just a collection of beam elements right now, and so they're all just lines and edges. Okay. But once we mesh it and once we apply the boundary conditions, you'll actually see these as beams. Okay. All right, so the first thing we're going to do is we're going to mesh. Okay, and we don't need to do anything special with the mesh here, and so we're just going to apply a default mesh. Okay. And so the only thing we have to do is make sure that we're using a quadratic element because this is a static structural, and we always want to make sure we use quadratic elements for that. Okay. And for the element size, let me go ahead and change the units here. Let's change the units to inches. Okay. I'm going to use an element size of 25 inches, and let's see what that generates. Okay. All right. So let's go ahead and generate the mesh. And we end up with a mesh that looks like this. Okay, we could check the statistics of the mesh, and this mesh is really coarse right now. So if you can kind of see from here, 25 inches is pretty big for this kind of the structure. Okay, so let me go ahead and reduce this quite a bit. Okay, and so instead of 25, let me try 10 inches. Okay. Because I want the element count to be kind of somewhere in the what's called in the thousands. Okay. All right, so that's still a little bit too big. So let me go ahead and lower this. Let me go ahead and go down by a lot. So let me try 2 inches. Okay. Okay. And then we end up with a mesh of 1666. Okay. So let me go down a little bit more. So actually, let me go 0.5. Let's see what that does. All right, so with a mesh size of half an inch, then we end up with a mesh that looks like this, and we have about 6,626 elements. Okay, so I know in the project in the activity specifications I say it should be 7,500, but so anywhere around this ballpark is fine. This project isn't that sensitive to the mesh, but I just want to make sure that we have a good density on this thing. Okay, all right. And so that's the mesh. And so there's not much to do with that. So was everyone able to open up mechanical and get a mesh on this guy? Okay, good. Okay. All right. So the next step is going to be our modes and constraints. Okay. So the first thing we're going to do is we're going to fix the structure. Okay. And so let's go ahead and right-click static structural. And we'll insert a fix support. And to help you select the bottom parts, you can go ahead and change this to the node selector right here. Okay, and we're going to select the four nodes on the bottom, which are going to be the ones connected to the ground. Okay. All right. So there's our fixed support. Okay. All right. Next thing we're going to add is we're going to add standard Earth gravity. Okay, and so that's going to add a load onto the structure. And so the structure has to support its own weight, and so that's what we're going to do with that. Okay. Next, we're going to add some force nodes. Okay, and we're going to add force nodes on three different locations. Okay, so the first one we're going to add is a compressive load on top. Okay, so let's go ahead and right-click on static structural A5. Let's go ahead and add a force. Okay, and I'm going to select both of the two nodes that are on the top here. Okay. So you should have both of these selected. All right. And let's go ahead and change this to components. And we'll make the Z component of the force here minus 5,000 pounds. Okay. And let me go ahead and rename this force. So let me rename this force to be, what did I call it? Call it axial mode. Okay. And so the reason I call it axial mode is because, you know, if you look at, you know, most of the elements in this truss are vertical to some extent, right? I mean, some are slanted and such. And so applying a vertical mode on top is going to put everything into compression more or less. Okay. All right. And so the next thing we're going to add is a transverse mode. Okay. And so let's go ahead and right click static structural A5. And we're going to add a force. Okay. And so this transverse mode is going to be applied on the length of a member. Okay. And so we're going to switch to edge selecting mode up here. Okay. And then with edge selecting mode highlighted, go ahead and click one of these members on top. Okay. It doesn't really matter which one that you pick, you know, because it's very symmetrical. But I'm going to go ahead and select this one out in front right here, in the front left. Okay. All right. So we're going to be applying a force on this entire beam right here. Okay. And just like before, we're going to apply this using its components, and we're going to apply a force of 100 pounds. Okay. And so you should have a horizontal force of 100 pounds going that way. Okay. Right. And so this is going to be a transverse mode, and so I'll call this transverse mode 1. Okay. And so the reason I'm calling it transverse is because it's acting perpendicular to the beam. Okay. All right. And so the next load that I'm going to add is a load on the bottom. Okay. So let's go ahead and right click, add a force. Okay. And we're going to add a transverse load onto these beams here on the bottom. Okay. And I want you to do on two parts of this. So I want you to do on the entire length of this beam element here. Okay. And so you're going to have to hold control and click for the top part and the bottom part of this beam. Okay. And then the magnitude of this force is going to be a minus 100 pounds in the x direction. Okay.
Professor, which leg is it?
Yeah.
How do we tell which leg it is?
And so it should be the one that's, you know, if you're viewing it such that you know, your top one is this one in the front left. Then the bottom one should be applied on these two. So the ones that kind of go from the foreground to the back, yeah, from the top to the bottom. So it might help to kind of view the truss like this, and then, you know, it's going to be the one that goes kind of diagonally.
Yeah, fixed constraints on all four of the legs, or just one?
All four of them. Yep. Mm-hmm. Okay. Let me go ahead and rename this. This is transverse mode. Transverse mode 2. Okay. All right. So any questions so far on the loads that we're applying?
Oh, sorry. Which length should we put on the transverse mode 2?
Yeah. So transverse mode 2 is going to be this one right here. So it would help if you kind of view the truss where it's kind of like you're kind of in this isometric view. And so it doesn't matter which isometric view you do. And so if you want, you can just click on this. Oh, okay, that didn't help. And so you kind of view it so that it's kind of like, you know, where you have kind of one corner that's kind of out in front. And so which one that you choose is not as important, but it should be relative to the first one. And so the first mode is this kind of part of the triangle right here. And then the second mode is being applied on, you know, the one that's on that. So the corner of this one should be the same as the corner of your first mode. Yeah. Mm-hmm.
The corner of the first one should be the same corner of the second one?
Not the same corner, but it should be on the same side. And so because the first one is
where it's attached to that crossbar.
Exactly. So if you it kind of makes like a pattern like this. So if you look at the first line, and then you follow that around, you go horizontally on this one right here, and then you end up with the bar on that side.
And we're selecting the whole edge for both.
Exactly.
Okay.
Yeah. So you're selecting both the top portion and the bottom portion. Yeah.
I'm sorry. Could you just say the magnitude one more time for the two?
Yeah.
Transverses.
So the top for transverse mode 1, it's a positive 100 pounds in the x direction, And then for transverse mode 2, it's a minus 100 pounds, minus 100 in the x direction.
Positive 100 and then minus 100.
Exactly. Yep.
And then they should be connecting at that same crossbar.
Yes.
Okay.
Yep.
Thank you.
Yep. All right. So everyone got the modes okay on this one? Okay. All right. And so now let's go ahead and look at the results. And so we're going to insert total deformation just like we normally do. Okay. And because this is a this is kind of a unique situation where we have all these slender beam elements, ANSYS actually has a special way to display results because what we're interested in is we're interested in seeing what elements of these are in compression and which one of these are in tension. Okay, and so we can go ahead and right click on solution A6 and then go to insert, and then we have this tool right here called beam tool. Okay. And so we're going to use this. Okay, and so the beam tool will give you a bunch of specialized results that are unique to beams. Okay? And the one that we're going to be interested in the most is something called the direct, what they call the direct stress. Okay, and the direct stress, direct stress measures the stress that's in basically within the same line as the beam. Okay. All right, so let's go ahead and add that. Okay, and then let's go ahead. Let's just go ahead and solve for now. Okay. And so hopefully it shouldn't take too long because this mesh is not that big. Okay. And so when the mesh finishes, or when the simulation finishes, you should see a deformation field that looks like this. Okay. And if you don't want to see the mesh, because the mesh kind of gets in the way of the results, you can go to results up here and then go to edges and then click on no wireframe. Okay. And so with that, it'll be easier to see the results. Okay. All right. And so you should get results that look like this with a maximum deformation of about 0.2952. Okay. And then if you click on the beam tool right here and you look at direct stress, you can see what the stresses are like within this beam or within this trusses. Okay, and so negative direct stresses mean that the elements are in compression. Okay, and so all of the blue elements here are basically going to be in compression. Okay, while the red here will show elements that are in tension. Okay, and so that's going to be useful for us because that's going to give us some hints about which elements are going to buckle first. Compared to the other ones, okay? Because remember, the more compressive stresses that a beam is experiencing, then the lower its bending stiffness is going to be. Okay. All right. And actually, there's one more result that I want you to find. Okay. And so if you go ahead and right-click solution A6, okay, and then you go to insert and then beam results, and then there's one more result called axial force. Okay. And if you read the tooltip here, then you can see that this inserts a result field that will evaluate the force along the beam element axis. And so this is kind of another way to express, whether the beam is in compression or in tension. Okay. Let's go ahead and add that. We're going to evaluate our results. Okay. Right. And so this is just another expression of the same thing. Okay. So if you look at the color pattern between axial force and direct stress, you'll see that they look identical, right? And so the colors here don't change at all. The only thing that changes here is the numbers. And so, axial force expresses the same results, but the units are forces, okay? But direct stress just expresses it in terms of stress units, which is PSI, okay? All right. And so if you want to take the screenshots for this now for the final report, what I'm asking you for is the total deformation. I'm asking you for the axial force, and I'm asking you for the direct stress, okay? And so you can go ahead and take those right now if you want and save it in documents just so that you don't have to do it, later, okay? All right, any questions on this so far? Was everyone able to get these results? Yeah.
Would you say the colors mean for the compression and tension?
Yeah, so a negative, if you look at the direct stresses or the axial force, a negative number means that the member is in compression, and then a positive number means tension.
Okay.
Yeah. Mm-hmm. Yeah.
For me, I think my results look different. I think slightly different. I'm not sure what I did wrong.
Okay.
Like for me, that little X for you, it's like bowing in, mine is bowing out.
Okay, let me take this moment to kind of walk around and see. But if you got these results, you can go ahead and take the screenshots, and you can go ahead and move on to problem 2. Okay, and so problem 2, I'm having you observe the stress stiffening effect. Okay, and so the only thing, just make sure when you move on to problem 2, you have to turn on large deflections. Okay, and so go to analysis settings and turn on large deflections. Okay. And then from there, I'm going to have you vary the axial force here, from negative 10,000 to 1,000 to 10,000, and you're going to see how the deformation changes. Okay, and so if you got through problem 1, then you can go ahead and start working on that, and then I'll make my rounds and help people out in the meantime. Okay.
Oh, I know. So I forgot to change this to negative 100.
Oh, okay.
Oh, and then I have something I need to talk to you about.
Okay. Yeah. It's under analysis. Yeah, axial load is compressive. So these forms should have 20. Oh yes, yeah. Should be. Yeah, I think probably yours is just kind of put around. Yeah.
Yeah.
Yeah, that's not the same Z. It's still acting perfectly parallel to the actual flat surface of the wall. So
Right, so
the wall's getting pulled that way.
Right, so you can only apply axial modes that are perpendicular to that wall. And so the axial mode you have to do separately with the net force.
So yeah, just do it, just a force thing, and then also select the inner surface of that. Okay.
Yeah.
And at first I was like, there's no like flat surface for it to like push against, but I guess it's just the whole inner tube being pulled
Yeah.
off that direction.
Yeah.
Okay. So you press
Yep.
You don't need a screenshot of us varying the loads, right?
Of clearing of what?
You don't need a screenshot of us varying all the loads, right?
Oh, no.
Maximum tension, maximum compression.
Yeah. Just maximum tension, max compression.
Yep. First and last.
Yep. All right, how's everyone doing? Everyone can see the stress stiffening effect, right? And so this is kind of a bigger example of the beam case that we talked about on Monday, right? And so if you we're keeping the transverse modes exactly the same, so those are not changing. And so for the axial, the only thing we're changing is how much axial load we're putting on this. Okay? And so if you compare the results for when you have the truss at maximum tension. And so maximum tension is when we apply an upward, 10,000 pounds, okay? Then you can see the total deformation is only about 242 inches, okay? But if you change this to a compressive load, and so if you change this to minus 10,000, okay, go ahead and hit solve, okay? You can see the total deformation has gone up by a pretty significant amount, so over 50%, right? And so now the total deformation is a 0.396 inches, okay? And all that is just due to the stress stiffening effect, right? Because if you compare the case when you have maximum tension versus maximum compression, right? It's the exact same amount of force, right? And so they're both at 10,000 pounds. The only thing that's different is the direction. And so because the direction is compressive, then the bending stiffness of our elements is actually going down because of that stress stiffening effect. Okay. All right, and so that's kind of the buckling effect in action, right? And so that's why when you have any kinds of compressive loading on your structure, it's always good to check for buckling and stress stiffening. Okay. But it can take a while, right? Because if you want to continue this, and so at this point, we probably are not at the point where we're at, we're not at the point of failure yet. Okay. But if you wanted to continue this and see how much more you have to increase this in order to reach failure, it could take a while because then you'd have to change this manually. You'd have to change the axial mode, and it's a little bit cumbersome. Okay. What you can do instead is you can use the eigenvalue buckling module within ANSYS in order to get that information very quickly. Okay. And so I'm going to go ahead and close mechanical for now. Okay. I'm going to come back to Workbench. Okay. And we're going to use a new toolbox here called Eigenvalue Buckling. Okay. And so you're going to take this and you're going to drag it onto the solution part of your static structural. Okay. And so if you do that, then you can see it's going to create a new eigenvalue buckling part here, from which we can just double click on setup. Okay.
So you put it on top of the solution box?
Exactly. Yeah. And let's hope that this works. We don't have a repeat of the modal analysis. I dropped it onto solution.
So did we need a running solution in our mechanical or in our model before we can run this?
It would help, yes, to complete a solution. Yeah. All right, and so if you drag the eigenvalue buckling onto solution, then you should be able to come up in mechanical, and you'll see a similar interface. So you can see all of your boundary conditions and mesh should still be here. The only thing different now is that we have eigenvalue buckling. Okay. Okay. And really, there's not much to this. So because we've already included the loads, okay, and we've already included the all the mesh and everything. All we really have to do is just hit go on this, okay. But we are going to change things, okay? And so first thing we're going to do is if we go to analysis settings on eigenvalue buckling, it's going to ask you how many modes that you want to find. Okay, so let's go ahead and increase this to 6, okay, just so we can find 6 modes. Okay. Right. Another setting that I want you to change is I want you to go to this setting here called include negative mode multiplier. Okay. And we're going to say no. And so what that setting does is that, in the case when you have a tensile mode, then ANSYS can find, say that if you reverse this, the mode direction, this is when, that's when you would reach buckling. Okay. And that could be good for a very complex structure. We have very complex moding where you're not really sure, is this thing going to be ultimately compressive or ultimately tensile? Okay. But for this case, it's relatively simple where we know it's going to be a compressive load. And so we're just going to sit no to that. Okay. One other thing that you need to make sure before you move forward is that if you go back up to your axial mode, you want to make sure that this is some negative number. Okay. It doesn't matter. It doesn't really matter what the negative number is, but we just need to make sure that this is a compressive mode. Otherwise, it's not going to find any buckling modes at all. Okay. Okay. All right, and then that's it. And so all we have to do now is we just have to hit solve, and we'll let it do its thing. I think it's resolving my my static structural first. Okay. Oh, I guess it just solved my static structure. So let me go ahead and solve my eigenvalue buckling as well. Okay. And we get an error again. Unknown error. Ah, okay. So this looks like it's the same error that would happen during the modal analysis, but for everyone else, was everyone able to get results when you solve the eigenvalue buckling? Okay, great. And so I'll just ad-lib this just because it's not working on my computer. Okay. And so when you complete the eigenvalue buckling analysis, if you click on solution right here, okay, what you should see is a table of buckling multipliers here on the bottom right. Okay. And so does everyone everyone able to run it? Are you able to see this table right here? Yeah. And it should be like a row of 6 different multipliers. Okay. And in fact, it should look like this. Okay. Your exact numbers might not be the same as mine. And in fact, I don't remember when I produced this document what I used for the mode. But remember, this is a multiplier on which if you multiply all the modes in your previous static structural, this is what the multiplier has to be in order to get buckling. Okay. And so for the case that I ran in my office, I only had to multiply the modes by 1.72. And then that's going to give me buckling. Okay. All right. And so one other thing that you can do is that once you get those numbers here, you can go ahead and highlight all of them. Okay. And just like we do in modal analysis, you can right click on it. And then when you right click, you can click on the button for create mode shape results. Okay. And then after doing that, you should see 6 more 6 more deformation fields appear here. Okay. And if you click on them, you can view what the buckling modes actually look like. If you only have 2, you can go to the analysis settings under eigenvalue buckling and then make sure that this number is 6 right here. And so if you only have 2, just make sure that this is 6. Yeah. Okay. All right, and then just like before, and just like we saw with modal analysis, you can click on each individual mode just to see what the shape looks like. But remember, don't take the actual deformation values in those shapes seriously. And so remember, those are only simply just to show you the shape. But the actual deformation, you actually have to apply those modes, in your static structure. Okay. And so if you're interested, what you can do is you can take the multiplier that you get, and then apply that multiplier to all of your modes. Okay. And so not only your axial mode, but it has to apply to all the transverse modes as well. Okay. And so if my multiplier was like 1.72, I would take this minus 10,000 and multiply by 1.72. And so it'll be minus 1720. Okay. For the transverse mode, this would be 172. Okay. And then for the other transverse mode, it would be, instead of minus 100, it'd be minus 172. Okay. And then you can go ahead and solve it again. Okay. And then you can view, and you can then view the results. Okay. And so I think for this one, then buckling did indeed occur, because I increased my load by a factor of 72%, but then my deformation increased by like 2.5 from before, right? Because remember, the old deformation for this used to be 0.39, but now that the deformation is 0.85, that's more than 2 times that. And so when you have the deformation exceed your amount of the amount that your deformation grows exceeds the amount that your load grows, that's a good indication that buckling has occurred. Okay. And so unfortunately, I won't know what the actual buckling multiplier is for this one because it's not working, but you can give it a try on your own as well. Okay. All right. And so for this part of the problem, I want you to show me the table of multipliers that you got. Okay. So give me all 6 of those numbers. And then I think I want you to show me all 6 of the mode shapes as well. Okay. All right. And so why don't you guys go ahead and work on that? Okay. And after that, then the rest of the activity is just playing around with this. Okay. And so problem 4, I want you to repeat everything from problems 1 through 3, but I want you to change the material. Okay. It can be a lighter material. It can be a stiffer material. I'll leave that up to you. But so far, we've only used structural steel. Okay, so you can go ahead and work on that for problem 4. And then for problem 5, I want you to repeat everything 1 through 3, but I want you to change the loading configuration. Okay, and so right now the loading configuration is we have an axial mode, and 2 transverse modes. Okay. And so you can either add an additional mode to here, or you can change, the location of one of these modes, just change the loading, somehow. Okay. And I want you to repeat and see what you get from the buckling analysis. Okay. All right. Any questions on any of that? Okay. All right. And so we have about 35 minutes left in class. And so, I'll, if you have any questions on anything, just raise your hand and I'll come by, and then just go ahead and go ahead and work. Okay. All right, there's a question in class, and I'll come back. Yeah, so go back to and so I just want you to keep on the value, and so right now it's maximum. And so what I want to do is right now, so the maximum detonation is 0.2. And so I want you to change the axial mode. So let's go ahead and change it. Let's change it to minus 9. Okay. And then go ahead and run it. Okay. Check the folder. And you can see that my deformation went down. And so let's change it to actually maximum. Actually, you have a part of it. Okay, so let's change this to draw. And what you should see is that the deformation is. And so this is all part of the stress. So what I want you to do is that I want you to create a graph where you on the x-axis you have you should go minus 10,000. You should see that at minus 10,000, your deformation should be maximum. And as you increase the load in it, it's like then deformation. Yeah, in increments of 1 depth. Minus 1, minus 10,000, minus 1,000. Let's check. See that it's way less. Yeah, and so that's the stress. So yeah, so go ahead. Yeah. After I add in all the buckling. Did you turn on large deflections, Aaron? So did you go to analysis settings here and make sure that large deflections are on? And so, okay, so you add. So the what do you mean when you add in the buckling deformation? So when you created the 6 mode shapes here, even your regular deformations look no different. Do you want to share your screen? I think that might be a bit easier. Oh, I have to enable it. Sorry. Go ahead. Okay. Yeah. So these so what you're viewing here for the six, those are just the shapes of the buckling modes, and so we haven't actually applied those multipliers onto the structure, right? Oh, your multipliers are less than 1. Oh, that's interesting. And so when I say to apply the buckling multiplier, what I mean is take, let's take the first mode. And so the first mode was 0.68, right? So do you see that in the bottom right of the screen? Yeah. And so you're going to take that multiplier, and then you're going to multiply that by all the different mode values. And so if you go to Axial Mode, and you're going to multiply that minus 10,000 by 0.68. And so it'll be minus 6,800. And you're going to do the same for the transverse modes as well. Yeah, so it has to be for all the modes. Yeah. And so what this is basically saying is that you actually reach buckling before the structure would buckle kind of before all that stuff. Yeah. Yeah. So this would be the first point of buckling for you. Yeah. Yeah. It's interesting. It's interesting that it's less than yeah. So remember, so when it's solving the buckling problem, it's solving a linearized version of the buckling. And so, but when you solve it for the static structural, you're solving like a nonlinear problem with the large deflection. And so you're not going to see the exact same deformation. What the eigenvalue buckling is that's a prediction of if you put the structure out in reality, then that's how it thinks that it will buckle. But the equation that it's solving for in the eigenvalue buckling is different than the one it's solving for in static structural. Yeah. Yeah, so this is fine for this, and so the eigenvalue buckling is just it's an approximation. So it's an approximation of how it thinks it's going to be. But yeah, but the actual one that you actually see is actually a bit different. Yeah. Mm-hmm.
Okay. For the number 3 right here, where you ask for magnitude. Okay, you're asking to show the load multiplier, but we're asking to show screenshots of the deformation multiplied by the load multiplier.
I want to see the shape.
That's
Okay,
so,
so you don't want me to apply this.
no. That was just if you were curious. But even then, you know, when you apply it, the deformation actually doesn't even look like this. It's what it's doing here is that it's saying that this is the member that's going to fail, and this is what the shape looks like. So it'll break basically, which is actually not.
You're saying then we don't really mean anything, but if
No.
you see, so if I apply this load prior to this first condition here.
Yeah.
And I see this, you said almost double in magnitude, then there's a good chance that it will buckle.
Yeah. So when buckling occurs, so like when you're doing the stress stiffening test of button 2, you saw that the line was between. And so as you change the axial mode, once you reach a buckling point, it's going to kind of shoot up.
Okay.
Yeah.
Well, probably back to that.
Okay, here's your I know you looked at it.
Oh, thanks.
So I forgot it on Monday, but I saw it.
So, wait, so are these all the axial loads, or not the axial loads?
Yeah, so these are predictions of where the buckling is going to occur. And so basically this just shows you what the shape of the structure is going to look like right before it.
But are these all black? Is this all? Oh, so this multiplier is added to the total. It's added to all 3 of these at one time.
Exactly. All the modes.
So basically, if it's multiplied by almost 2.4, then we know that this leg right here, this piece is going to fail.
Yeah. So these are a multiplier on the loads that you've already applied.
Okay, so what I'm looking at is 10,000 times that.
Exactly.
Okay.
But you're also multiplying the transverse modes too. So actually one part of the activity I want you to try to is to actually remove the transverse modes.
Right.
Because if you remove the transverse mode, that's a little bit of a better indicator. Because if you see this, then the buckling multiplies because the transverse mode is kind of messed up. Because you increase the amount of bending from the transverse modes, of course it's going to burst. But a true buckling test, you only got a compressive mode, and what's the point at which you don't? That's kind of true.
So taking out the transverse load, which did right now, will increase your take out the transverse load, your chance of buckling will increase.
No, so your structure can sustain more load. So the buckling multipliers are increasing.
Right.
And so that means that you can increase your load by more before.
Okay, yeah, so, yeah, they did. Okay.
So this is basically telling me that if I multiply the total loads by 4.2, basically, that now it's going from failing in the legs, and if the force is so great now that this top structure is completely failing.
Yeah.
Okay. And then the rest of it will crumble with this thing.
Exactly.
Okay. Okay. That's pretty interesting. But and then you said right that this isn't totally accurate, so we need to kind of test it versus our actual static structure.
Right. But if you look at the first one, so if you look at the first deformation, yeah, so you can see it's only failing with one length. So actually, someone asked me this on one too, and I just kind of. So if you actually apply the loads, it's not that you're going to see no deformation everywhere else. It's just that the only one that's going to fail is that. And so the shape that you're viewing is that it's telling you this member, this part only is going to buckle, and then everything else is going to be. That's why you see. But if you actually apply that load onto your static structure here, you're going to see deformation everywhere. But the only one that's actually going to buckle is
So basically, there's at this multiplier, like there's a chance that this structure might live.
Yeah.
If the safety factor is good enough.
right. So the eigenvalue buckling actually overestimates these. Actually, in reality, it should it'll buckle sooner than this.
Okay, so these represent what would buckle given the multiplier.
Exactly.
Right.
Exactly.
Okay.
Yeah, if
Yep.
That's the lowest. So.
Right. So most of the time you're only really interested in the first one because that's the one that's kind of causing the break. But if you do have a situation where you apply like a huge amount of load at once, then just the shape of the button will get lifted. So that's kind of the purpose of it. But you're right. Most of the time you're only interested in the first. Because if you go past the first one, then you're not going to see the rest of the structures. Just yeah. So if you go past that first one, your structure is doing it anyway, but it's just the shape of it, which could be important too. If you're doing like demolition of something, then you know if you want to break in a certain way, that could be most of the time. Yeah, exactly. Just use a question. Yeah. Yeah, I have a problem with that. Yeah, I want to see the graph, and so I want to see the graph of the x-axis. We have axial load and y-axis definition. So I want to see that flow, but then you don't have to show all this. So just maximum tension, maximum pressure. Okay. Yep. Exactly. Okay. So for the Eigenvalue Buckling, you don't need margin deflection. You only need margin deflection to see stress different problems. So most of the time, you only really interested in just the first one. Usually, if you repeat that whole, then you know it can become structure. Most of the time, you're only interested in. Yep. Yep. Yep.
The definition shape was a big something.
So remember these are just the shapes, and so these aren't true deformations. And so you know don't take these numbers seriously. So the only thing that you should see these shapes for is just you know this is just what they're going to look like. So actually go change instead of true scale because these numbers are means, right? So do the auto scale. Yeah, and so if you do true scale, then it looks kind of crazy. But you know, in order to actually get numbers that you can trust, you actually have to apply an oscillating mode like this. And so that's what the harmonic response is. And so actually, a few people have asked me about harmonic responses. I'm going to put together a handout for next week. But these are just the shapes, and so you don't take these numbers seriously. So these numbers are only going to be there just to show you this is going to deform more than this one, but it's not a true deformation until you actually apply it. Also,
so even if I turn on the true scale, it doesn't mean
it doesn't mean it. Yeah. And I hate this because it'll say units right here, meters, but that doesn't. But that's I think that's ANSYS. It makes you think that it's something meaningful, but it's actually not. It's just yeah. Okay. Yeah.
I'm not sure, but I can try to choose a scale on one other. Yeah, so if you, but I make it once it reflects the true situation.
Yeah.
I mean, like, because the other scale, like, scales down, there is some fire a lot. So it's only like good for this case because this right. So what this means, these are all modes. So if you take this number and you multiply by all your modes, that's going to cause buckling. So since your multiplier is less than 1, that means the structure is buckled. Even before these modes, 77%. And where it comes from. And so if you try 76% of the node, then it's going to follow like this. That's the one that's going to follow. Yeah. So that means you would have to multiply the modes in order to see buckling shapes. You have to multiply the mode, all the modes by 1.3. Yeah.
This question is same.
Yep, exactly. Perfect.
So tension, just like less than.
Exactly.
Just than,
Stress stiffening. Yeah.
Okay.
And you're actually seeing a little bit of buckling here. So buckling, so you can see over here, the graph is mostly like follows one slope, and then right here you can see it's starting to uptick, right? And so this is probably where buckling occurs. So actually, if you look at your mode multipliers, it's probably in somewhere in the ballpark of 0.6, 0.7. That's probably when buckling is going to occur. Somewhere around.
Multipliers are 0.6.
Exactly. Yeah. And so you're seeing that exactly right there. So, so the first sign of buckling is when that graph kind of goes from one slope to a slope. So if you do get a situation where you apply a load, because right now we're applying the loads kind of gradually up, but sometimes you can have a load that just gets dropped onto your structure. And so if you have a load that exceeds the first one by this much, then this is what the buckling will look like. And so if you look at some of the higher modes, you'll see like failure in multiple members. So for the lower ones, usually it's just one member. But if you look at the yeah.
I was wondering why there's like different, like each like
Yeah. So these shapes actually only tell you which members are going to fail. And so if you click on 6 or something like that. 6. Right. Well, that's a weird one. You click on 5. Oh, okay. Oh, it's interesting. Everyone's getting very different results.
So I was wondering like why are they all different ones?
Yeah, it's because those are the points, because buckling is defined when you apply compressive load and the bending stiffness essentially goes down to 0 or goes down to a very small point. And so
I have this stuff about
okay.
Compression, right?
Yeah, it has to be in compression. Yeah. That's why things are getting.
Yeah, I can do that. Good. Right.
Yeah, you have to do it separately.
But I saw on the legs before.
Yeah, it should be in the
Legs. All right. So yeah, so there you go. You got one here.
yeah, so check the higher ones now. Yeah.
Oh,
Yeah. So you see, like when you apply a load that's like really high at once, then you're gonna have failure in multiple members. So, like for the lower ones, you only get failure in like one of these. But then for higher ones, you get multiple failures.
Then you're saying that this only highlights the one that will fail
Exactly.
first. So if these guys can be bumped as well.
They could, but not nearly as much as this one. So this is the one that's actually gonna like crumple and fail.
And then this one is crumbling just because of location.
Yeah.
And
The
this
location
one-
of exactly. Yeah. So because of this configuration of forces, this is the one that's experiencing the most compressive forces. So that's the first one.
So from a design standpoint, you would hope that it can withstand
all of these. So you would design it around the first one. So you want no buckling at all. And so, yeah, so really the one that's most useful 99% of the time is just the first one. And so you want to make sure that, you know, your buckling multiplier, you can consider that like the factor of safety. And so if you apply like a load on here, you want the multiplier to be like 3 or 4 or 5. And say like, I can increase, you know, this load can still increase by a factor of 3 to 4, and you can still launch it. But, I mean, this is a unique case because these are less than 1. Usually you don't want this because that means your structure's not buckled already. But most of the time you want this, you know, over at least over 1, but you know, higher the better.
Yeah, so if you tested this multiplier out and the force you expecting is larger than what this would give you, then you can say, oh, this is way too weak.
Exactly.
Okay. All right.
Aaron, are you still there? Signed off. Okay, no problem. Yeah.
You want the pre-stress or the stress for the
It doesn't matter. It's either.
okay, cool. I'll tell him neither.
either is okay.
Yeah, it doesn't matter. So you can either use stress-free or pre-stress. You know, you can just choose one, but you don't have to do both. Yeah. All for homework. So the 6 modes don't have to be within a certain range, but the I think for the last one, then that one has to be within that one has to be around 200 hertz. Yeah. So it's just the first one, not all 6. That would be crazy. Yeah. Oh yeah, all 6 would be crazy. Yeah, just do the first one. Yeah. That's the lowest one anyway too.
Professor.
Hey, what's up?
A quick question. So on when doing the modal homework, I just had a question about resonance.
Yep.
And you know how we were talking about how the loads, the geometry, and the mass are like major factors on depending the natural frequency.
Yep.
So I noticed on the homework, the part, certain geometry, like the housing itself, has more influence on the frequency.
Yep.
I just wanted to get like more of more of an input, like why does the housing have more influence, or is it everything in combination, like the whole structure itself, or is it because I'm not too sure. I'm just trying to kind of analyze it in a way where like, why does the housing have more influence on the resonance? Like it peaks higher when I just adjust the housing more than any of the other parts. Like
The reason for that is because the housing is kind of in a very central location on the part, and so a lot of the other parts kind of attached to that housing, and so any change that you make to the housing is also going to change the vibrating properties of everything beyond that too, right? And so whenever you change something kind of central to that, then it affects everything it attaches to. Yeah.
Oh, I see. And the modes that are generated, that you said, that's not the actual the deformation itself, but it just shows just the displacement, like fields, like how the housing would change more than any other part.
Exactly right. So those are just the shapes, and so yeah, those deformations are not true because we haven't put any kind of vibrating load onto it. And so in order to actually see what the actual magnitudes would look like, you would have to put like a vibrating load. And so you'd have to like turn on the engine or something like that, and have the engine kind of start vibrating. That's the only case where you'd be able to see that. Yeah.
Okay, so the deformation fields that are generated in the modes, those basically like where it has like the higher magnitudes, that's basically we disregard that. That as not actually
exactly
what's happening.
Right. So you can view those and say that the gearbox or whatever structure you have is going to deform like this, and so the shape is going to look like this. But the actual magnitudes of those deformations, that depends on what kind of loading that you apply onto it as well. Yeah.
Oh, okay, so the locations of the deformation, like the red spots, that is true.
That's true. Yes.
Okay.
Yeah.
Okay.
But the actual amount that it deforms, that's not true. So you actually need to do like a harmonic response in order to see that.
Okay. Yes. Okay. Awesome. All right. Thank you, Professor.
Yep. All right, so we're just about out of time today. Of course, you guys are free to stick around. You know, I know a lot of you are working on previous activity and this activity and final projects, and so you know, I'm fine with you guys sticking around here. But you know, this is more people than usual, so you know, I just want to say that you know, if you are the last person that's in here, just make sure that you close the door. It shouldn't lock automatically, and then just turn off the lights. Okay. All right, so I'll stick around if you have any more individual questions. I'll come around and answer those, but that's kind of the end of our class section. So thank you guys for coming for the last ANSYS activity of the year. And so, you know, from here it's just working on stuff. And so, oh, I forgot to put the poll. And so, or did I put the poll? I put the poll already, didn't I?
Yes.
Okay, so the poll is out there already. And so, you know, please vote in the poll. In addition to that, I've gotten quite a few people asking me about harmonic response. And so that'll be the first thing that we do next week. And so I'm going to put together a quick handout for that. So that will cover that. And then after that, I'll go off the poll and then see what people want to see. Right. So thank you everyone for coming. I hope you enjoy the rest of your evening, and I will see you next week.
So Professor, what I wanted to talk to you about is my group partner for biomechanics signed us up for our project.
Yeah.
And he got the last slot on Wednesday.
Okay.
And then somebody stole our slot.
Yeah, I got an email about that too.
I changed it back to us. I changed and I put a comment like, don't change it again.
Yeah.
That's just what I put. Okay. But I just wanted to let you know, just in case they do try to change it again.
Yeah, I got.
Yeah, it's just so slimy, honestly. So
I'm sorry about that.
It's not your fault, but like, you know, it's just like you should, you know, yeah, you can change it, but like you should be honest enough to just be like, okay, I didn't get the slot.
Yeah. Thanks for letting me know. I mean, I was hoping that wouldn't happen. I mean, I've done this, you know, 2 semesters now and haven't had an issue with it, but you know, when I haven't recently like that. Yeah, thanks for letting me know.
Okay, thank you.
Yeah.